Today I will continue teaching about the period of mass spring system. So first we are going to study how mass, stiffness and the amplitude affects the period of mass spring system. So how mass, amplitude and stiffness affects this period of mass spring system. Assume that we have two systems, but both systems have equal stiffness, which means same spring constant and amplitudes. Let's check the restoring force first. What is the equation for restoring force for mass spring system? Negative kx. Because both systems have the same amplitude, restoring force will be equal for both systems. And acceleration. To get the acceleration, we are going to divide the restoring force by the mass. So F over m1 is the acceleration of the heavier mass. Because m1 is greater, acceleration will be smaller. So that's why heavier mass will have a smaller acceleration than the lighter one. Because mass of the lighter one is m2 is smaller than the m1, that's why acceleration of the smaller mass will be, or lighter mass will be greater. But both will travel equal distances because they have equal amplitudes. Distance traveled by the heavier mass and distance traveled by the lighter mass will be the same. Then if we think about this, their distances or amplitudes are equal, distance traveled by the masses are equal, but heavier one has a smaller acceleration. Smaller acceleration means time of travel will be longer. So longer travel time, what does longer travel time mean? Longer period. So heavier mass will have a longer period, but lighter mass, because their amplitudes are equal, distance traveled by masses are the same, but lighter one has a greater acceleration, which means it will travel in a shorter time. So that's why the lighter mass will have travel in a shorter time, and that's why it will have a shorter period. So then we can say that yes, mass of the mass spring system has an effect on the period. The heavier mass causes a longer period, while the lighter mass, shorter period, but heavier mass, longer period. As mass increases, period of the vibration also increases, heavier, longer, lighter, shorter. Second parameter which we are going to study is the spring constant, which is elasticity. Systems will have equal masses, so masses are equal, amplitudes are equal, but stiffness, yani spring constants are different. First system has a spring constant K1, second system has a spring constant K2, and first system is stiffer, spring of the first system is stiffer, spring of the second system is less stiff, so K1 is greater than K2. So, but masses are equal. First one has a mass m, second one also has a mass m. Let's check the restoring force, negative kx. First system has a greater spring constant than the second one. First system will have a greater restoring force compared to the second one. But for the stiffer spring, yes, stiffer spring will have a greater restoring force, but less stiff spring will have a smaller restoring force. What about the acceleration? Because their masses are equal, when we divided forces by mass, stiffer spring will have a greater acceleration and also a greater restoring force. Less stiff spring will have a smaller acceleration and also smaller restoring force. What about distance traveled by the masses? They are equal because amplitude of both systems is a. Equal distances is traveled by stiffer spring with a greater acceleration. If acceleration is greater, which means time of travel is shorter time of travel. What does it mean? Shorter period. So that's why stiffer spring will have a greater restoring force. Not only greater restoring force, also greater acceleration. Equal amplitude, they travel together with the less stiff spring, and because greater acceleration, So equal amplitude is traveled in a shorter time. However, smaller acceleration, so less stiff spring will have a smaller acceleration. That's why distance traveled by this mass will be longer. So longer period for less stiff spring, shorter period for stiffer spring. Then we can say that a stiffer spring causes a shorter period. As stiffness K increases, period of the vibration decreases. And last quantity is the amplitude. So identical mass spring systems, K's are the same, springs are the same, identical springs. Even masses are the same. Only we changed the amplitude. First system is vibrating with a smaller amplitude. Second system is vibrating with a greater amplitude. Now let's check the restoring force. Because first system has a smaller amplitude, so restoring force acting on the mass will be smaller restoring force for the first system, but for the second system, because amplitude is greater, so the restoring force will act on the mass. Then we will now check the acceleration. So smaller restoring force will result in smaller acceleration because mass of both systems are the same. Smaller restoring force will result in smaller acceleration. Greater restoring force will result in greater acceleration. If we check the distance traveled by the object, because one system has a greater amplitude than the other one, so the one which is smaller amplitude will travel a shorter distance. Remember, for one cycle, distance traveled by the object was a plus a plus a plus a, which is 4a. But for a1, because a1 is smaller, mass of the first system travels a shorter distance, but mass of the second system travels a longer distance because a2 is longer than a1. Now check. Shorter distance, smaller acceleration, traveled with smaller acceleration. Longer distance, traveled with a greater acceleration. What does it mean? The effect of two decreasing quantities, smaller acceleration, shorter distance, cancel out, and period remains the same. Or the effect of two greater quantities, two increasing quantities, again cancel out, period again remains the same. Then we can say that amplitude of the mass spring system has no effect on the period of vibrating mass spring system. And if as a result, so mass has effect on the period, yes. Amplitude has effect on the period, no. Spring constant has an effect on the period, yes. So these two quantities has effect on the period of the mass spring system, but amplitude has no effect on the period of mass spring system. So a change in mass affects the period, a change in spring constant affects the period, but a change in amplitude does not affect the period. That's why these two quantities will include in the equation of the period of mass spring system. Equation will be 2 pi inside the root m over k. Now let's solve some problems. One of the section of question. A 0.75 kilogram mass attached to a vertical spring stretches spring by 0.3 meters. What is spring constant? So this is the unstretched spring first. And after that, you are going to suspend from this spring an object. So you will observe that this spring is stretched by a distance which is equal to 0.3 meters. And the mass of this suspended object is 0.75 kilogram. Of course, this mass will apply some gravitational force on the spring, and this force will stretch the spring, which is equal to m times g. M is 0.75, g is 9.81. So let's multiply them. 0.75 multiplied by 9.81, which is equal to 8.4 newtons. So 8.4 newtons is the applied force on the spring, and amount of stretching is given as 0.3. Spring constant, let's calculate the spring constant. We know that K is equal to applied force divided by amount of stretching, F over X. Applied force is 7.4. Stretching is 0.3. So when we divide 7.4 by 0.3, we will get the result as 24.5 Newton per meter. And part B, the mass spring system is now placed on a horizontal surface and set vibrating. What is period of the vibration? Let's write the equation for period 2 pi inside the root m over k. So 2 pi is 6.28. M is mass of the object is 0.75. And the spring constant is 24.5. Take this into bracket. So let's do the calculation. 1.1 second. And next problem is the body of 1,275 kilogram car is supported by on a frame of 4 springs. 2 people riding in the car have a combined mass of 153. When driven over a porthole in the road, the frame vibrates with a period of 1.84 seconds. For the first few seconds, the vibration approximates simple harmonic motion. Find the spring constant of the single spring. There are 4 springs, one in here, second one in here, third one, and the fourth one. So they are identical springs K, whose spring constant K and K. Because there are 4 springs, so this equivalent spring constant is K equivalent is equal to 4K. So first, let's find the mass. Total mass is mass of the car. Also, there are some passengers. Mass of the people. When we add them, we will find the total mass of the car. Total mass 1 over 1,275 is mass of the car. Combined mass of the 2 people is 153. Let's add them and then find the total mass. 1,275 plus 153, which is equal to 1,428 kilogram. This is total mass vibrating together with this spring, and period is also given. Period is 0.84 seconds. So we are going to calculate K. What is the spring constant of each spring? There are 2 ways. One of them is you can first calculate the equivalent spring constant. After that, you calculate spring constant of each spring. This is what I am going to do. So T is equal to 2 pi root of mass total divided by equivalent spring constant. Because we are going to calculate this equivalent spring constant, so that's why we should square the equation to get it out of the root. T squared is equal to 2 pi squared m total divided by equivalent spring constant. So cross product T squared and K equivalent. So K equivalent is equal to 2 pi squared mass total divided by T squared. Let's insert the given into the equation. So 2 pi 6.28 squared. Mass total is 1,428 divided by period is 0.84 but squared, almost 80,000 Newton per meter. This is equivalent, but there are 4 springs. 4 times K is equal to K equivalent. So then 4K is equal to almost 80,000. So divide by 4, divide by 4. So you are going to get the spring constant of one spring, almost 20,000 Newton per meters. So this is all for the section 2. We will continue in the next lesson, section 3.